Now that we're familiar with the factors that influence 1,2 versus 1,4 regioselectivity, I'd like to take a look at a couple of specific examples that demonstrate this regioselectivity in action. Before we start, I just want to remind ourselves of the reduction of an alpha-beta unsaturated carbonyl system with a non-selective reagent. And so we learned that whenever we treat this enone with sodium borohydride and isopropanol, we're going to form two different products that reflect both the 1,2 addition and the 1,4 addition, followed then by the 1,2 addition. Right? So we can say that this reaction is a non-selective reaction. And that sodium borohydride by itself is a non-selective reagent because it can't fully distinguish between these two positions. The hydride is being added to both the beta carbon and the carbonyl carbon. So we're getting very little regioselectivity with sodium borohydride. So how do we accomplish these reductions regioselectively, right? How can we accomplish a reduction that can reduce just the carbonyl? And in contrast, how do we accomplish a reduction that can reduce just the double bond? Well, let's first look at the Lusch reduction. So the Lusch reduction is kind of a reaction that builds on sodium borohydride reduction and just adds a little sprinkle of catalyst in there in order to make this reaction selective. So rather than just using sodium borohydride, and we'll use an alcohol solvent. I won't specify isopropanol, we'll just say some alcohol solvent. And then in addition, we're going to throw in catalytic cerium chloride. Well, this reduction, which is called the Lusch reduction or Lusch conditions, is going to affect the 1,2 selective 1,2 reduction of this alpha-beta unsaturated ketone. Let's think about why this is happening, right? It's good to know that these reactions can happen, but my objective for you is to make sure you understand why this is happening. Well, let's think about what that cerium chloride is doing. Maybe pause the video and try to understand what the structure or the composition of cerium chloride might tell you about the reactivity of that catalyst. Hopefully you can understand that cerium chloride is a metal center, cerium center, surrounded by 3 electronegative chlorine atoms. And so as a result, that cerium chloride, or that cerium metal center, is going to be Lewis acidic. Remember, the definition of a Lewis acid is an electron pair acceptor. And so what happens whenever this is sprinkled into the reaction is that that Lewis acid is going to be able to interact with the carbonyl oxygen and in effect activate that carbonyl carbon towards nucleophilic attack. Right? That's going to cause that carbon to have a significant partial positive charge. And because we're amplifying the positive charge on that carbonyl carbon, that sodium borohydride is going to be way more attracted to it than it normally would be. As a result, when the nucleophile adds to this system, the hydride H-, right, which we're taking from sodium borohydride, would much rather add to the carbonyl carbon over the beta carbon. And so the cerium chloride activates the carbonyl towards nucleophilic addition. We see this strategy in other reactions where they're trying to impart selectivity onto a conjugated carbonyl system. They'll sprinkle in a little bit of a Lewis acid. Often this Lewis acid is cerium chloride, and that allows addition to occur, not just hydride addition, but other additions to occur selectively in a 1,2 fashion. In contrast, right, so we've learned about 1,2 reduction of alpha-beta unsaturated ketones. Let's think about 1,4 reduction of alpha-beta unsaturated ketones. And for that, we're going to look at copper hydride. And copper hydride we can think of as a copper attached to a hydrogen. And I'm going to put that in quotes because this is not the actual structure of copper hydride. It doesn't exist just as a 2-atom molecule. But for the illustration of the properties of copper hydride, this is good enough. And what we want to get out of this is that copper hydride is just like any other metal hydride in which the metal hydrogen bond is going to be polarized towards hydrogen, giving hydrogen a partial negative charge, and then the metal a partial positive charge. Now the reagent that we're going to use to deliver that copper hydride is a reagent called Strykers reagent. And Strykers reagent is actually a copper hydride that is complex to triphenylphosphine. So phosphorus with 3 phenyl groups around it, and that acts as a ligand or something that sticks to the metal center that can allow it to have organic properties, right? Bring it into the organic solvent. So we have a triphenylphosphine ligand attached to a copper, which is attached to a hydrogen. And then this is actually organized as a cluster of 6 molecules, and so we call this a hexamer. And then these reactions are often carried out in anhydrous solvent, we'll just say THF. And when this happens, the hydride is going to be delivered to the beta carbon in a regioselective fashion. And so this is a way, copper hydride is a way of specifically reducing one in a 1,4 fashion over a 1,2 fashion. Now, copper hydride is not used as much as sodium borohydride or lithium aluminum hydride, but whenever we need to reduce in this regioselective fashion, it is often the go-to reagent for these types of reductions. The structure, again, if we think about it, we have a phosphorus with a lone pair and 3 phenyl groups attached. And that is going to be sticking to a copper center, which is then attached to a hydride. And it's this ligand that can bring all of this into an organic solvent and allow it to interact with other organic molecules. So these 2 reactions show us how we can selectively reduce alpha-beta unsaturated ketone systems. The loose reduction allows 1,2 reduction, whereas copper hydride is going to allow us to selectively reduce in a 1,4 fashion. Similar to copper hydride, where a hydrogen is attached to copper, we can also make organocopper reagents, where carbon is attached to copper. So in this reaction, what we're going to do is we're going to take a Grignard reagent, say phenyl magnesium bromide. This is a reagent that you've all made in lab. And we are going to treat this with a catalytic amount of copper chloride. And then when the reaction is done, just like any other Grignard reaction, we're going to do a Protic Quench. Well, whenever we mix phenyl magnesium bromide with copper chloride under these conditions, and we'll say we can do this in THF or some ethereal solvent, what happens is that copper is going to give the Grignard a special property where it adds specifically to the enone in a 1,4 fashion. right? Whenever that happens, the phenyl group is delivered to the beta carbon, the electrons shift all the way up to oxygen, and then that intermediate is held there until we do the water quench, the protic quench, and then we quench the enolate and get to the product. Right? So what's happening here is whenever we mix phenylmagnesium bromide and copper chloride, is we're getting a transmetallation where the phenyl group ends up leaving magnesium and sticking to copper. And just like copper hydride is regioselective for the beta carbon, in this case, this phenyl copper is also going to be regioselective for 1,4 addition. So at this point, you might be realizing that copper is doing something kind of funny or something kind of specific to whatever is attached to it, right? Either a hydrogen or a carbon. And it's doing that to make, or the property that it's imparting on that nucleophile is it's making that nucleophile a soft nucleophile. And that is really a special property of copper. And the reason why it does that, or the reason why we can think of it doing that, is if we compare it to a magnesium, an organomagnesium compound, a Grignard reagent, we know that the magnesium carbon bond is going to be heavily polarized towards carbon. So a lot of that electron density is going to be sitting directly on carbon. Copper is not going to be as electropositive as magnesium, and so that copper-carbon bond, or in this case the copper-hydrogen bond, will not be as heavily polarized towards that hydrogen or carbon. And so copper is going to be able to share that electron density with either hydrogen or carbon much better than magnesium will, or much better than lithium will. As a result, because that electron density is more evenly shared, these copper nucleophiles are going to be much softer as nucleophiles and are therefore going to be selective for addition in a 1,4 sense. Finally, let's look at the addition of enolate nucleophiles. And we learned in the last video that enolates are considered soft nucleophiles, particularly when we're starting with enolates that form from 1,3 dicarbonyl systems. Right, so we know that if we take this 1,3 diester and we treat it with sodium ethoxide, we're going to be able to deprotonate at the carbon in between the carbonyl groups. Remember, the pKa of one of those protons is going to be 13, and so this is a reaction where we're using an ethoxide base or an alkoxide base, but we're able to fully deprotonate a carbonyl and form an enolate. And so the equilibrium is going to lie, in this case, towards the enolate. Right? Realize that whenever this enolate is formed, that electron or that negative charge can exist on this oxygen here, the central carbon where the proton was plucked, or the other oxygen, right? So that electron density is very diffuse, very delocalized, and as a result, this is going to be a soft nucleophile. So when we add this nucleophile to an alpha-beta unsaturated system, it's going to add to the beta carbon rather than to the carbonyl carbon. And then whenever we quench this reaction, with an acidic workup, we'll be able to protonate the resulting enolate that forms from that beta addition and make our product. And so in this reaction, this is the bond that was formed from the addition of a nucleophilic carbon developed from an enolate to a beta carbon of an alpha-beta unsaturated ketone. One of the reactions that I would like you to know is a reaction called the Robinson Annulation, or you'll commonly hear it called the Robinson Annulation. Annulation or annulation comes from a Latin word that means little ring, and this is a reaction that is used to make ring systems which are common in natural product chemistry. This is a reaction that was developed in the 1940s by a British chemist named Robert Robinson, who was later knighted for the work that he did. And he actually won the Nobel Prize for his work in chemistry. And this is one of the reactions that was he was given credit for in winning that Nobel Prize. You can see in this reaction what we're doing is we're taking a ketone and an enone, or an alpha-beta unsaturated ketone, mixing them with base, and we're making an annular system or a ring system. All right, so we're taking a 6-carbon unit here, a 4-carbon unit here, and in the product we have 10 carbons in that product, right? So you can see how these two things might be adding together. It's important to note that the Robinson annulation or annulation is actually a combination of two reactions that you already know. The first is going to be a Michael addition. And the second is going to be an aldol condensation. Remember, an aldol condensation is an aldol addition followed by the loss of hydroxide or the loss of water, the dehydration of that aldol product. All right, so this series of reactions is going to give us this product. Knowing that these are the two reactions involved in the product formation, see if you can draw a mechanism that accounts for the formation of the product from these starting materials. Pause the video, and then when you're done, restart the video, and we will take a look at the mechanism together. So let's take a look at the mechanism. We're going to start just by drawing out our two starting materials. And we're going to treat those starting materials with base. In this case, we're using potassium hydroxide. You can use any alkoxide or hydroxide base. Ethoxide is a pretty standard base to use, but just for simplicity reasons, we're going to use hydroxide in this reaction. And I'm not even going to write out the potassium ion, I'm just going to draw out the hydroxide anion. And then we need to understand that the potassium cation is there to counterbalance any negative charge that forms in the reaction. If you look at this hydroxide can do many different things, right? It could pluck a proton from this carbon, it could pluck a proton from that carbon, it could add to that carbonyl, it could pluck a proton from this carbon, it could add to this carbonyl, or it could add to the beta center. And realistically, this hydroxide is probably going to do all of those things, but only one of those things is going to be able to get us to the product, okay? Remember that the two reactions involved in the overall Robinson annulation are Michael addition followed by an aldol condensation. Michael addition is the nucleophilic addition of enolates to the beta carbon of an alpha-beta unsaturated carbonyl system. And so in this case, we need to make that enolate, and we'll do so by plucking a proton off the ketone and forming our enolate. Now that we have our enolate nucleophile, that enolate nucleophile can be added to the beta carbon of the alpha-beta unsaturated ketone. I'm going to draw the product a little differently here, but I will make sure to keep track of the atoms that are involved. Right, so if we look at this alpha-beta unsaturated ketone, and we say that the carbon of the alkene is carbon A, B, and then the carbonyl carbon is C, and then the terminal carbon is D. Here we have A, B, C, and D, right? So you can see we're making a carbon-carbon bond between the alpha carbon of the ketone, or the enolate carbon in this case, and the beta carbon, or carbon A, as we've drawn it here, of the alpha-beta unsaturated ketone. Now, if you look at this, hopefully you can start seeing how we're going to get from here to there, realizing that we've already done a Michael addition, and now we have to do an aldol condensation. If you're keeping track of the atoms, hopefully you can see that we need to connect atom D to the carbonyl carbon. And in order to do so, we need to effectively do a proton transfer between atom D and atom B. All right, so what we're going to do, in the first step, we made water by deprotonating the ketone. And so here we can use that water as just a proton source. And we're going to put a proton on carbon B. And then the hydroxide that is formed when we deprotonate water is going to remove a proton from carbon D. Right, so if we're trying to connect this carbon to that carbon, remember, all of the reactions we've learned in this class involve a nucleophile and an electrophile. So we need carbon D to be nucleophilic. The carbonyl carbon is always going to be electrophilic. So once we remove that proton, we've formed our nucleophilic carbon. And now we can use that nucleophilic carbon to add to the carbonyl. And this is going to make our 6-membered ring. You can see we're making a 1, 2, 3, 4, 5, 6-membered ring. I'll map my atoms here still. And then draw the product. So A, B, C, and then carbon D made a bond to the carbonyl carbon. Whenever we added to the carbonyl carbon, we lost that pi bond, and so now we just have a single bond and an oxygen with a negative charge. Again, in this step here, we formed water, and so we can use that water to protonate the alkoxide that forms in this reaction. All right, so we're almost there. So if you take a look at this intermediate and compare it to the product, hopefully you can see that the only thing we need to accomplish is a condensation reaction. So there are two ways to accomplish that condensation, right? We learned that if we take this reaction and we heat it with base, we'll be able to affect that condensation or the elimination. We can also do this under acid. This reaction is being done in base, and so we will use those basic conditions when we write out the mechanism. So again, in this step, we formed hydroxide, and so hydroxide can be used as the base to pull a proton. And when we do this, we're not going to show the direct elimination, but we have to recognize that whenever we pull a proton alpha to a carbonyl, that is going to form an enolate. And so we need to show that intermediate formation whenever we draw the mechanism. Even though we're trying to get to this, right, we have to show that the structure of the intermediate is stabilized through resonance. Right, now that we've formed the enolate intermediate, we can push those electrons down, push these electrons down, and then kick out hydroxide. Right, and so we got rid of hydroxide here and formed water. In this step, we are once again forming that hydroxide anion, and then this gives us our product, right? And if we take a look at that product, hopefully we can see where each of the starting materials is contributing to that overall product structure. Right, so this would be D, C, B, A. So these 4 carbons were part of the alpha beta unsaturated carbonyl. And then we can say 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right, so you can see the connections that were made whenever we ran these 2 reactions. Right, this connection here was made through a Michael addition, or a 1,4 addition of an enolate to an alpha beta unsaturated carbonyl. Right, we connected the enolate of the ketone to the beta carbon of the alpha beta unsaturated ketone, whereas this bond here was made through an aldol condensation. Right, where we connected carbon D of the alpha beta unsaturated ketone directly to the carbonyl of the ketone, of the cyclic ketone, right? And then that pi system was formed through the condensation or the elimination of hydroxide. Now these are just a few of the specific reactions that allow regioselectivity in the addition of nucleophiles to alpha beta unsaturated carbonyls. There are many more that we could look at, but in the interest of time, I think we're just going to end here and then move on to nucleophilic aromatic substitution in the next video.